Hello, wonderful people of the internet. One second, let me see. Am I live? Yeah, I am live, but I accidentally just turned off the music. So let's turn that back on, shall we? I hope you guys are all having a wonderful day. So today, we're going to be continuing with the Fractal Flame saga. Do I actually have the? Let me check really quick. I didn't even check. Okay, cool. So the title is correct. Let's talk about what the plan is, and yeah, what we're doing, and then we're gonna hop right into it. So first thing I'm gonna do is cd into projects, algorithm archive, ls here, cd into. Actually, I'm in the wrong directory. cd into videos, iterated algorithm archive, iterated function systems, ls here, and now let's just run mpv Sierpinski Hutchinson over here. So this is a typical animation that I've been showing as of late for the generation of the Sierpinski triangle via something known as an iterated function system. The idea is that we start with 3 points, A, B, and C, and we have 3 functions, one that will bring your point halfway towards A, another that will bring your point halfway towards B, and another that will bring your point halfway towards C. With 3 additional points, D, E, and F, we can then have all 3 of these points generate children that follow one of the functions that we prescribed. So the idea is that, you know, we'll have some kids move in all of these directions, and then if those kids have kids, they'll generate new points that move like that, and if they have kids, they look like that, and more kids, and more kids, and more kids, and more kids, eventually until you get this Sierpinski triangle. And this is kind of the heart of an iterated function system. Because we have the 3 initial functions, no matter how we iterate through those functions, we will eventually find ourselves on the attractor, and the attractor here is known as the Sierpinski triangle. Delphi becoming fractal IRL, what are you up to? I'm going to talk about that in just a second. So let me open up Zernal PP, and let's talk about Zernal PP, and let's talk about yeah, what the plan is for today's stream and subsequent streams after this point. So the title is Becoming a Fractal, right? A fractal, right? And there's a lot of bits to this, okay? So what you just saw was a very simple diagram of what's known as an iterated function system. Recently, we've been doing CD projects, Flamify, ls, Mirage, save, whatever, doesn't matter, 1.png. Recently, we've been creating images that look like this, which are something known as Fractal Flames. So the idea here is rather than just having one function system, we have multiple function systems that you can choose between, and they create a whole bunch of different patterns and stuff like that that look really cool. This is all the same set of flames, and here's a different set of flames. So essentially we have these function sets that have completely variable, basically transformations and things like that that we can do with the function sets. So you have what is essentially an n-dimensional space, where n can be however many function sets you have, whatever the transformations for those function sets are, etc., that you can traverse. So what I'm interested in doing is basically using an image as some sort of cost function. That is to say, if I put my face down as an image, I'm then going to try to figure out the optimal set of function flames in order to basically recreate my face as a fractal. And that's the idea. I want to basically become a fractal. I want to set my image in and then vary through this n-dimensional space until I found the perfect set of functions such that we then have our fractal flame image. Now, this means that we're going to have to hit a whole bunch of notes that we've covered on this channel before. In fact, pretty much all the notes that we've covered on this channel before. We're going to talk about fractals. We're going to talk about, you know, genetic algorithms. We're going to talk about parallelization on GPUs. We have a lot to talk about here. And today, we're actually going to be talking about convolutions. Because here's the thing, for the fractal flame method, you'll note that some areas, like this area up here, have way fewer points than areas in here, right? And so what we're doing today is we're going to have a blurring function, a function that will make it so areas that have very few points end up being blurred more than areas that have a lot of points. And this should allow for us to generate images in a way that looks a bit prettier, you know? So for example, going back to this image in here, note that out here, there aren't very many points around. So we just want to kind of blur those areas so it kind of looks like there are points around, even if there aren't. Meanwhile, areas in here, we still want to be very sharp. So that's the idea. We want to basically create a convolutional kernel that varies in size depending on how many points are around. So we're doing the first step first, which is basically creating a convolution. And we got halfway done with our implementation last time before I kind of had to leave. So hopefully by the end of the day, today, we'll have an implementation of a convolution, hopefully with a variable filter width, And yeah, we can go from there. So again, if you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I can see it in chat. Oop, sorry, wrong one. This over there. That I'm going to Control C here. And I'm just going to have the fractal up in the upper left-hand corner, so that if anybody, is trying to figure out what we're doing, I can just talk about it. Yeah, so sorry I didn't stream over the weekend or on Friday. On Friday, I had a literally 6-hour meeting, which doesn't happen much, but when it does, I was just shot. I was not in any mood to do a stream after that. So I kind of just said, you know what, we're going to take Friday off. And then Saturday and Sunday, I was actually working on other things, and I just wasn't able to muster in me the ability to do a stream. Even today, I'm still kind of in a funk, but I figured, let's just do it. Usually it's like jumping in water, like, if you're going to swim, you got to jump in eventually, right? And, the fear of jumping in the water, that little, I don't know how to put it, the trepidation there, the hesitation before you jump in, that's usually the worst part, Like, once you're in, you're used to the water and everything like that, and that's kind of how it was with me, how it is with me in streaming. Like, mustering up the courage to get that stream started is usually the hardest part, and then after that, you can just go for hours and it's not a big deal. So today's going to be a 2-hour stream. Again, just kind of doing 2-hour streams, at least for today, tomorrow, and Wednesday. On Thursday, I might consider doing a longer kind of Thanksgiving stream, and on Friday, I might do a longer stream as well. It just kind of depends. I'm trying to figure out how I want to balance, my work life and everything like this. And also, I am going to have a conversation with someone on Wednesday about potentially... it's both potentially a new job opportunity and a discussion of where I can actually foreseeably bring my content in the future, all of this kind of stuff. So I'm probably going to have a different opinion Wednesday than I do today or tomorrow, but we'll see how it goes. So let me go ahead and open up that image. Let's just do Mirage. What am I looking for? Save something, 1.png. Move this up here into the corner. And yeah, we should be good to go. So this will just be up there in the corner. Something like that should be fine. Perfect. Move this over here. Great. So if we want to flip through all the different images, we can. I like this one. This is my favorite one. I don't know why I like this one so much. I just do. Let me get some water and then we'll go ahead and get started. Again, guys, chat seems super quiet right now. So if you have any comments, questions, concerns, anything like that, feel free to let me know. Otherwise, we're just going to hop into the kernel and start breaking things. Again, guys, I have been thinking a lot about how to make the stream a bit more approachable as of recently, specifically because we have these kind of lulls. Recently, for the past few weeks, we've been in a bit of a lull. And again, this is just because I haven't been able to stream consistently, and I've just been super tired. And it's my fault, really, more than anyone else's. But I've been trying to think of ways to make the stream a bit more engaging, and I came up with a few ideas this weekend. That was partially what I was doing this weekend. And so I'm gonna maybe try to do some changes to stream. Maybe not soon, but in the near future. Does that make sense? Not like next week, but maybe in the next few months, I'll start implementing some of these changes. It's not going to be like all of a sudden overnight, like the stream's dramatically different. But I am hoping that by, maybe middle of December, January, or something like that, the stream will be a bit different. Just followed your YouTube channel? Oh yeah, cool. Thanks for that. So let's go ahead and CD into projects, F Flamify in here. And now we're just going to run Julia _project. And now let's just do using revise and then using F Flamify, and it should build, I think. I don't remember if I left it in a state that would build or not. That's okay. We'll figure it out. But yeah, the YouTube channel is genuinely fine. Like, there's not an issue with the YouTube channel. It's just the whole ecosystem doesn't really make that much sense. My YouTube channel has what, 75,000 subscribers, 73,000. I actually don't know how many. 72,000 subscribers, which is pretty good. Like, honestly, having a YouTube channel with 72,000 subscribers is pretty dang good. The issue is that if you have a YouTube channel with 72,000 subscribers, you kind of expect other platforms to be doing well as well, and they're just not. So this says to me that people are not very engaged with my content as I would expect them to be. So that's why, again, this upcoming video is going to be like genuinely one of the most, I'm hoping the best video I ever make, as I do with all my videos, right? But this one in particular is just a huge combination of like an insane number of different things. Maverick Twitch, you just missed it. I'm so sorry. It takes a few minutes to explain. But do you see this image up here? So this image up here is a set of different fractal function systems put together. Here, let's actually go to this image. So you see how we have like a heart in here? So we have one function that basically creates a heart, another function that kind of swirls the heart around, which is why you see kind of a phantom heart in here, and maybe another one over here. And so we have a bunch of different functions put together in order to create this thing that's called a fractal flame. The idea is that this fractal flame will generate, can generate really any image we want. And so what I want to do is I want to eventually read in an image and output a set of fractal flames that basically recreate the image, but in a fractal form. And so the becoming a fractal thing is basically creating a filter that will create a fractal flame-y image from any image that you read in. And that's kind of where I'm going. So right now we're working on a convolutional aspect of it, and then we've got a bunch left to do. So like this is going to be really, really hard. What makes it a fractal? What makes it a fractal is the fact that we're iterating through an iterated function system. Again, see, this is why I don't like doing all of my I don't like doing all of my intros like the moment I start stream. I always do all my intros for like the first 10 minutes of stream. And so you guys came in on the first 13 minutes of stream after the first 10 minutes, which means I had already just done the intro. So then I have to do the intro again, but it's okay. So this all works on something known as an iterated function system. So let me open up a new terminal, CD videos. One second. Algorithm archive, iterated function systems. Here, and now let's just do mpv Sierpinski Hutchinson.mp4. Okay, so these all work on something known as an iterated function system. So we start with 3 points A, B, and C, and we have 3 functions. One that brings you halfway towards A, another that brings you halfway towards B, and another that brings you halfway towards C. So the idea is that by iterating through this function system, again, the set of those 3 functions, you can recreate, whatever the shape is that is attracted by those functions. That is to say, a function system, when you iterate through it, will generate a weird shape. So in this case, we have D, E, and F, all generating 3 children, all following one of the 3 functions. And then when they generate children again, and again, and again, and again, and again, and again, eventually you get this Sierpinski triangle structure. So that basically says that the Sierpinski triangle is your attractor for this system. Also, let me check something. So you can't quite see A and C, but it's there, I promise. And so what makes this a fractal flame is that it's basically following or like, it's using a similar iterated function system pattern. So we have a bunch of these function systems put together, creating a bunch of different attractors. Maybe put something like about or info. But does recursion always generate a fractal? Not necessarily, but, okay, so it's not necessary. All function systems will span an attractor, but that doesn't mean that they necessarily make a fractal, right? So for example, if you created a square, A, B, C, and D, and all of them had the same functions where, one will bring you halfway towards A, another will bring you halfway towards B, another will bring you halfway towards C, and another halfway towards D, that actually creates a random set of points. It does not actually create a fractal. I like fractals, but it seems computing intensive. What we just showed you was computationally intensive, but actually we played some tricks on the YouTube channel, and you can just go there. Here, let me just go there now to make it so it's actually pretty good. I actually quite liked that one. So let's go to YouTube. Oh, chotomate. Can't show you that one. My bad. I clicked the wrong button. Okay, so I should be live again. Sorry. So let me go here, and I just want to go to my channel, which should be over here, and then my channel. And then we can go to, how to make fractals with trees. So this one was the one where we did some tricks to make it so you could go through that function system much faster. I saw Stephen Wolfram doing the same for his new kind of science project. I don't really know. I haven't really seen him. I've been doing GIFs and SDF shaders. Yeah, so we'll be doing GPU computing, but not shaders. So just because Shaders are usually OpenGL specific, you know, and we'll be using kernel abstractions. Basically, I know Cuda. I don't know OpenCL. Well, okay, I do know OpenGL a bit. I know shaders, but I'm more familiar with Cuda and GPU computing than I am with shaders. He used some simple set of rules to generate complex shapes. Right. It's kind of a similar notion, but honestly, I wouldn't compare anything that we're doing here to anything Stephen Wolfram is doing. Not because like what we're doing here is way below Wolfram or anything. It's just that he's, okay, in some sense that's true, but he's looking at a fundamentally different beast, I think, than what we're looking at here. Like here, what we're doing is actually still genuinely new research. It's stuff that no one's done before, but that doesn't mean that it's at the same level, you know? So we'll see. Yeah, also, I don't know, like, it does kind of get you down, right? Like, these series are, I don't know, let me see what we have here. Take a look. I don't have an Instagram. Yeah, looks good. Yeah, nice. Good job. Okay, so let's just keep going from here. So I'm going to open up a new file, and we're going to do, let's see, VI source, and I think it's going to be in image tools where we have the convolution. So here I have my convolutional sweep. Oh man, this is, we've got a lot to do here. If everything came from hydrogen, then probably the simplest set of rules that became this complex universe. If everything came from hydrogen, then probably it's just a simple set of rules that became this complex universe. I don't know if I necessarily agree with that statement, right? Because saying everything comes from hydrogen is already a bundle of complication, right? Like, you know, hydrogen is like, well, first of all, not everything came from hydrogen, right? Like a certain amount of stuff, you know, came from hydrogen. And you could argue that all, you know, atoms are kind of similar, but, you know, still you have protons and neutrons and electrons. It's just kind of like, that's a weird level of abstraction to take, you know? And hydrogen, yeah, like High Altitude said, hydrogen is also very complicated already. So it's like, you know, you can say, like, for example, the cell is the fundamental building block of biology or of life, as they call it. But does that mean that because everything's built off of a cell, it's easy? Well, no, it's just that that's the abstraction that biologists take, you know? For computer science, you know, we take a whole bunch of, you know, similar abstractions, right? Like we say that, we just deal with bits and stuff, you know? What's the difference between CUDA programming and normal programming? For CUDA programming, you specifically are focused on programming the GPU, so the graphics processing unit. So you've got things that you only have to deal with on the GPU. So that would be like, for example, shared memory is a resource that you don't really have to deal with on the GPU. GPUs are intrinsically parallel, so you have a lot of parallel computing things that you have to deal with. It's just a different paradigm, right? So you have to think of things completely differently than how you would normally think of them. Something like a sum, like a parallel reduction, for example, is actually kind of complicated on a GPU, whereas it's stupidly simple on the CPU, right? So anything iterative or recursive, you really got to rethink how you do it. And so lots of things like that. It's just a completely different paradigm. So it's not really what's the difference. It's like you should think of like GPU programming as completely separate than CPU programming, and that the difference is that they are there's basically, we should be asking what's the similarity between them, in which case there isn't much between how you program one and the other. Most stuff did come from hydrogen. There was only that in helium and lithium. Oh, that's cool. I'm a passing physicist. Never used Julia. Yeah, it's okay. I like Julia a lot. It's I've been using it for most of my streams, and honestly, it's good. I'm a big fan. Let me get some water. In fact, I use it for work as well. I use it for basically everything nowadays. I kind of hate the fact that I've become so Julia centric recently. Don't get me wrong, we'll still do C++ every now and again, but honestly, just because I don't really have time to fiddle with other libraries and languages, I've just been hyper-focused on Julia, and I just don't like that as much. I like being kind of what is it, a polyglot when it comes to different languages, like having multiple languages that I can just use at any given point in time. And right now, I've been so focused on Julia, it's much better than Python. For the stuff I do, it's better than Python, but that doesn't mean for everything. What's the benefit of Julia over other languages for you right now? Julia is fast, easy to use, easy to write. So it's much easier to read and write than, for example, C or C++. And it's just about as fast as C and C++. The thing I don't like about Julia, and the reason I tend to fall out of favor with it, is that it's got kind of like a cult-like following, and it's really weird, Does it run on a VM? I guess. What doesn't run on a VM, right? I don't know. Comes with a ton of math libraries. Yeah, Julia does already, because Julia is primarily targeting like the Fortran, C, MATLAB crowd, so like scientific computing group, I would say. They would probably, people who are writing Julia probably argue it's for everyone, but for me, it's great for, people who are doing scientific computing. I mean, honestly, I don't know. I genuinely hate MATLAB, so anytime I see something kind of MATLAB-esque in Julia, I get kind of, a little bit pissed off. But on the other hand, you don't have to use the library. Like, the reason I don't like MATLAB is because it locks you into that. Okay, there's a lot of reasons I don't like MATLAB, but one of the reasons is because it locks you into using MATLAB structures. But here you can write your own, and in Julia you can write your own, and it's just as fast, so it's fine. Okay, so what do we have here? So this was my idea for a convolution. It's been a long time, and this is not quite right. So we have Convolution Sweep. We're saying n is going to be the size of the output. So we have an output image, we have a signal that we're reading in, and a filter. And I basically say, I don't know why I have this time domain comment. I can probably get rid of that. And let's see. So 4i and 4j are just going to be going through the sizes of the image. And then essentially what we're going to try to do is create a filter with a left, right, up, top, and bottom bound. And then we're just going to move through the filter. And ideally, we say we have some sort of residual sum. What is rsum? I don't even remember what rsum stands for. Let's just modify this so probably running sum or something like that. And then we're just going to go down here and say running sum. This is really dumb, but it is what it is. And here we're going to say running sum. And then here we're going to say running sum as well. Okay. Right, so the idea was I just wanted to do a sum of kind of whatever the filter is times the signal at the location. So like the idea is we find an up, top, bottom, left, right bound in the image, and then we just kind of multiply the filter by that. Now the issue was that in this case, here, let's explain the problem here. So let's do journal new page 4. Let's catch up on chat, and then we'll explain the problem. Let's go here. I hate MATLAB because they maybe use it in college, and I hate MATLAB and I hate college. Fair enough. Are you done with teaching now? I'm kind of done. I've got one more class to teach. Does Julia suffer from pointer problems like C or C++? Wait. Let me explain to you. No, Julia suffers from garbage collection issues. I wish Julia had pointers. Like if Julia had the same memory. Like, Julia would be a perfect language for me if two things were true. One, it had zero-based indexing, and two, I could actually use my own pointers. Because right now, because it's so garbage collected and stuff, like, it's a pain. It's a huge pain to use. Garbage collecting on the GPU is the worst thing in the world. Why did anyone think that was a good idea? Anyway, whatever. It's fine. I'm doing busy work to organize efforts to fix tagging in web game archival project Flashpoint, so I won't chat much. That's okay. Thank you so much for coming in. And also, like, yeah, sounds cool. Keep up the good work. Run some, running some. Gee, it's fine. I could have done that. Hey, Trash Talk, how are you? I'm a Rustasian. A happy... Oh, you use Rust, yeah. Voyard Klama, thank you so much for following. Really appreciate it. Okay, so let's talk about this. I'm going to draw a big... Here's our image. Image is going to be pink. All right? So on top of the image, we're going to have a filter, right? So, the filter is just going to be moving... essentially, it's going to be moving, across the image like this, and then it's going to go across here, and it's going to go across here, something like that. So it's just going to be moving across, and as it moves across, it basically multiplies every element in the image, sums them all together, and then says that the very center of this filter is going to be equal to, like, the very center pixel is now going to be equal to kind of the multiplicative sum of everything else. So that's the idea. Now, what I'm running into issues with is specifically what happens when the filter is maybe slightly off the image, you know? So that is to say, the center pixel is maybe here. Oh, well, yeah, maybe squares. Is maybe this pixel in here, and there's like a pixel here. Let's say it's a 5x5 filter. So what I need to do is I need to make it so the summation doesn't have to deal with this. Now, we could just do zero padding of the image. That's one way to do it. That's my last resort. I don't want to have to do zero padding of the image for two reasons. One, the filter size is going to change, and I don't want to make it so, you know, the zero pads are going to potentially be bigger. I mean, it's fine. If I know the maximum size of the filter, I can just zero pad by those amounts. But I was hoping to zero pad dynamically. That way I don't have to store extra memory and I don't have any issues with that. But again, zero padding is a last resort. We can do that. I'm good figuring out A-spell currently. Oh, A-spell is cool. I use it all the time. I'm a Python main. Need to have some documents spell checked. My head is stuck in Haskell mostly, university stuff. Yeah, Haskell is one of those languages I really should know, but I don't because I'm what you might call a noob. Anyway, I like the whole Python main, by the way. It's like, yeah, you know, like you're a main in some fighting game. Like I'm a Wii Fit Trainer main in Super Smash Brothers. So I hope everyone has a great day today. Here's a watermelon. Yeah, I hope everyone is having a great day, actually. And again, if you guys have anything to say, you guys want to rant, whatever, just feel free to do so. I've been trying to have more of a casual stream recently just because I've been so out of it, you know? One of my brony friends is tempting me to try Rust. Rust is one of those languages that I also feel like I should know, but I don't, you know? Like Rust and Haskell. Okay, so what are we doing here? We are going to say we have a... Okay, so what I'm trying to do now is I'm trying to say if the filter is off the image, then this means that the left bound is going to be... Hello? I'm trying to say that the left bound is here instead of here, okay? So that's what I'm trying to do. And that would mean that we're grabbing just these pixels in here. But that also means that, the filter itself, we're not going to be able to do the dot multiply anymore. So I'm just going to kind of mess around with this a bit and try to figure out what we have to do. So here we have the left bound. So the problem is the left bound is specifically an element on the image, when I think the left bound should be like a relative, right? So it should be, we're removing one pixel or something like that. So here we're going to say left bound is equal to bounds check of signal. So what does bounds check return? Bounds check returns, so we have the pixel. So what I think this should return is instead of... Okay, I need to think here. I'm going to do it such that, for now, we're going to have a filter size, which we know coming in. We know the filter size, because we're reading in the filter. And then I want this to return... I want this to return the number of pixels... Like, okay, so for example, if this is a 5x5, this is 5x5, right? What I want it to return is, I gotta think about this. Give me a second. Okay, so there are a couple cases that we have to consider. We have to consider these corners here, and then these corners here, right? So these are the cases we have to consider. Okay, so what I want to do is I want to make it so, it returns basically the number of pixels to the left and the number of pixels to the right that we want to cut off. That's what I want. So what we're going to say, if the bound is less than 1, we're going to return, if the bound is less than 1, we're actually just going to return, we're going to return what? What are we going to return? If it's less than 1, that means that, you know, so this is 1 here. I'm sorry that I'm kind of thinking aloud. This is 1. So then this is 0. So if it's less than 1, it's going to return... I want it to return -1. Oh, I got to think about this. Let me get some water. My head... The cogs in my head are churning. I just haven't quite... They're just not quite clicking, you know? Rust is also... Whoa, I missed a lot. Is tempting to try Rust? Well, use the tool you like, and that fits. Rust is also high on my list. Rust has been very nice to me for years. I'm already a devotee of the better JavaScript, so it makes some sense for me to learn the better C. Oh, but I don't really feel pressed to change if Python is doing you well. I don't think I'll ever switch mains. I'm too in love with Python's unique weirdnesses at this point. That's the thing too, right? Like every single language has its own like quirks, you know? And you just kind of get used to the quirks and then you're like, it's fine. Like that's my issue with Julia, right? Like I know the system so well that when things happen, I'm like, it's fine. And the nice thing about C as a language, not C++, but the nice thing about C is that there isn't really too much, like it's not weird. It's like when you look at it, it's like, I mean, pointers, I guess, are kind of weird, but it's not so bad. C++, on the other hand, can be really annoying. So I don't know, like I tend to like old, like C style C++ was my old favorite. But you know, I've been switching to Julia. I've been using Julia too long now. And it doesn't matter, right? Most people know that we do Julia on stream and it's fine. Okay. So we've got 0, 1. Okay, so if we're less than 1, we know if we're less than 1, what I want to return, I think, is, how am I going to read this? So we're going to say array. So we're going to have ij, right? And that's going to be this pixel here, ij. Let me color that in green so we're all looking at the same thing here. So this point here is going to be the point ij. Okay? And the range for this filter is going to be I minus, I guess minus bound to I plus bound, I think is what I want. And then it's going to be j minus bound to j plus bound. I think this is how I want to read it. Okay, so now if we do, let me see if I can spell bound correctly. Spoiler, I can't. Okay, so now if we I minus bound, I plus bound. So this means that bound is going to be of size filter of size filter over 2. Okay, and we're just gonna say that all filters have to be odd. I don't know. I might as well ask here, how do you remove entries from personal library in ASpell? I think ASpell creates a dictionary in your local like home directory. It's like vi.aspell. Yeah. So I think if you do aspell en, oh, I don't know what these are. Let's just go enormous here. pp prepl. Okay, so these are all, so this is like BitLogic changes to BitLogic, Jur changes to get, Gray changes to Gray. Ooh, okay, I chose American spelling, that's interesting. Okay, now let's see, what's the other one? PWS? Anyway, you can find all the things in there, so you can change it. MRS, thank you so much for subscribing for 8 months. Let's go ahead and put 8 Simul cows in chat. Simul cow times 8. What do you mean that one failed? That one seemed to work just fine. 1, 2, 3, 4, 5, 6, 7, 8. There you go. How are you? I hope you're having. Oh, wait a minute. I see which one you said. I see the one that failed now. I got it. I understand. Okay. But anyway, yeah, so Trash Hawk. Usually you can just directly edit the ASpell. Deleted chat because I'm dumb. Oh my gosh. Let me fix that really quick. Why am I so stupid? Okay. Glad nothing happened there. Okay, let's go ahead and clear chat. You found it? Good. Happy to hear that. Okay. So, yes, that's what I want then. So we're going to do the sum, and now we just have to find the bounds. So, also, what are you alsoing? Okay, so assuming we have the bounds, then this is going to be is I the inner index, so I plus bottom bound. Bottom bound. I's going in. Oh no, I got these all mixed up. Let me change this so that this is going to be I and J. All right, because usually J is for Y and I just want to make sure I did this right. So we're going to fix all these bounds in just a second. And then we're going to do I, so this is now going to be j for the y index plus bottom bound. Okay, so j is going to count down. The bottom bound is always going to be plus. Yep. And then it's going to be j minus top bound. Thanks for the Simul cows. And now we're going to do this one, which is going to be, oh, I need to think about this one as well. So this should be I plus left bound. No, it should be I minus left bound. And then I plus right bound. That should be right. So now we have the bounds here. So now we have to do the bounds check. And I think what I'm going to do here with the bounds check is I'm actually going to read in. Okay, so how is this doing? So the bounds check is reading in the signal, which has a signal size. And then it has a bound. Okay, and in this case, then I also want the filter. Okay, I see. I also need to think about how we're doing the filter as well. Okay, it should be. Okay, I gotta think here. It should be filter divided by 2. Okay, I'll figure this out as well. So we're gonna get this done. Just give me a second. I gotta. Thoughts are coming slow today. Anyway, I'm fine. I'm receiving a paper tablet. I pre-ordered like 6 months ago, and now I'm trying it instead of sleeping. Wait, a paper tablet? A paper tab? Are you talking about like a remarkable tablet? Like one of those that like feels like paper but isn't actually? Or are you talking about like... Just forgive me for a second. I'm gonna do something dumb. I'm Googling what a paper tablet is. Yeah, okay, I've been wanting one of these for a while. Yep. Yeah, remarkable. How is it, by the way? I've been wanting one of these for a while, and I haven't gotten one, but I've thought about getting one. The problem is, okay, so for me, I don't really need a phone, but I do very desperately need a tablet, right? Because I do a lot of like reading and annotating papers and stuff like that. Tablets are really useful because basically it replaced it. Like I used to have stacks that were like, if you stacked all the papers I had from my PhD up, it would be like 3-4 feet tall. Like honestly, I had so many papers that I read through during my PhD. It was insane. And then it just got replaced with a tablet. So now probably if you stacked up all the papers I read, including the ones that are stuck on my tablet, it would probably be like a 6 foot tall like stack of papers. Like I had an insane amount of reading that I did during my PhD. And that tablet saved me so much. Just maybe not money, but it just saved me a lot of like just hassle. It was so much better than anything else than just reading papers normally. So I'm a big fan of that. But what I don't need is a phone. Like I've rarely ever needed a phone. So what I want is a tablet with a data plan so that I can use it as a phone if necessary. In principle, I also need a phone number attached with it, and I need to be able to call 911, I suppose, in those cases. But yeah, I just want to, basically a tablet with a data plan is what I need. So if Remarkable 2 had a data plan associated with it, I think that'd be the tablet I'd go for. I just received mine and my significant other's tonight, so I haven't had time to test it fully, but it's quite cool. Yeah, I'm keep updating, because I might get one myself. Do you have a landline phone? I do not. I don't have a phone at all. Like just phones. I have a Skype number, which by the way I had up on the. But the thing is also like I don't understand. Like, okay, hear me out. And I know this is gonna be really weird. I know most people already know my opinion on this already. I just don't understand how people are so connected to their phones. Does that make sense? Like, if you have a device, I get being connected to a computer, right? Because a computer, you have a big monitor, you know, or at the very least your laptop that you have, you know, there. You can do so much with a computer, you know? Like you can do a lot of typing, you can play games, you can do programming. I don't know, there's so much stuff you can do with a computer. But there's so few things you can do with a phone, you know? And it's mind-boggling to me how people are addicted to it, you know? Like, what do you do with the phone? Do you just scroll Twitter or Instagram or Facebook or TikTok? I don't get it. And so I guess maybe it's me. I I'm not. I need my tablet, but my phone is mostly just like a wired one. Yeah, that's fair as well. You can do a lot on the phone if you install the right apps. Right, but the terminal apps just don't work. And what other app do you need? You know, like, I don't know. Like, and it doesn't have a good package manager either that I found. Maybe I was wrong. Maybe I didn't look for the right stuff, but I just couldn't find a good package manager for it. Like, there was the App Store or whatever it's called, the Google Play Store. But it wasn't, I don't know, it wasn't great. And also, all the apps are like very poorly optimized. You know, like, don't get me wrong, but like, Reddit, for example, very rarely loads on my tablet. Like, it takes forever to just like look at any comments. So I just tend to not use it. Um, Discord more so, actually. Yeah, so that's the other thing. I can't figure out how to type on a phone. Like, with my thumbs, it's hard. So I end up having to take my tablet, turn it sideways, and type with my fingers as if it's an actual keyboard. I'm kind of learning now that I'm probably like 60 years old or something like that. I think I'm just too old for the like phone generation. At work, it's mostly a Walkman. Okay, you've got me. What's a Walkman? Walkman. Oh, it's a music player. Okay, fair enough. Oh, they're super expensive. Oh, sugoi na. Anyway, and also YouTube and Twitch. Fair enough. Again, maybe Luke Smith is smiling right now somewhere. I should know who Luke Smith is, but I don't know who that is. Original Walkman, 1979. It must be 6 years old. What's a Walkman? Okay, you're right. I'm not. I must be younger than 60 years old. I kind of knew Walkman was about music, but I don't really listen to music, so I don't think I'd be like that into it. Such as Zoomer. Zoom. Are they called Zoomer? Wait, are Zoomers called Zoomers because they do everything through Zoom? Like, is that where Zoomer came from? Because they have to take classes through Zoom? What? Do you know what a record player is? Yeah, of course. My roommate has one. Generation Z? Oh, okay. It's not because they're currently taking school through Zoom. That's not why they're called that. No, absolutely not. I'm sorry. It's a pun on boomer. You're right. I knew it was a pun on boomer, but also I thought it was a pun on boomer because they went through Zoom. But also, why are they called Generation Z? Generation Z are demographic cohort succeeding millennials and preceding Generation Alpha, X, Y, and Z. So am I Generation X? No, which generation am I? I must be. I'm millennial, right? Wait, what? Okay, so here we have here. I am millennial. I'm pretty sure. Like 20 Alpha Z. So here's Z, 1997. Millennial is Generation Y. Yes, I'm solidly a millennial. Generation X. Okay. Because there are two generations after Generation X was the internet, Y was 2K. Named after Pokemon. Where's Gen Y? Generation Y is millennials. Generation Y, yes, Generation Y is millennials, right? So I'm a Zoomer. Zoomer is 1997 through 2012. Maybe my sister is a Zoomer? I don't really know. But yeah, no, I'm solidly in the millennial camp then. Well, okay, I might be a little bit on the younger side, but you know, end of X. That's fair. Let's see. I'm an honorary millennial. Can you be an honorary millennial? Also, oh, I see. 2020, this is the current age. Okay, Generation Alpha? They just decided to go Greek? What is this, math? I was born in 97. I don't really think the generations really have that much weight, by the way. I would rather prefer to live in Day Z than being Generation Z. What is Day Z? All right, let's Google that now. Day Z is my internet? It is a game. Okay. Released on Xbox One and PlayStation 4 in 2019. Millennials are the best. Sure, yeah, millennials are great. What's up with the Emacs emote? Generations are ideals and actions rather than ages, in my opinions. Sure. I really don't know, honestly. I don't know why we started talking about generations. I think someone brought up Zoomers. Yeah, Alkma. It doesn't matter. There's like no single person that is the perfect millennial or the perfect boomer or the perfect Zoomer or something like that. You know, everyone's different. Generations are also mostly made up. No. You shouldn't be sorry for that. It's fine. Rambling on Twitch is totally normal, specifically on my channel when I can't figure out what I'm doing with my code. But yeah, I hope everyone's having a great day. Less real and most made up things. Less real than most made up things. Right. I think that's probably true. Yeah, I don't know. I think people play into it too much, you know. It's a generalization of trends based on the ages of people. Right. Simul rants are cool. Oh yeah, I have a little screen now for any time I go too ranty. I think, yeah, there we go. Rambaleos. Just in case I get too ranty and it ends up being just like way too much me talking and stuff like that. I decided I would have one of those. Okay. So what are we gonna do here? Bounds check. I just screwed up as well. That's what I get. Okay. Oh no, I shouldn't have done that. Oh, I have to rewrite stuff now. It's okay. We'll figure it out. So this was. Oh no, I didn't save before I screwed up my code, and now I have to. That was my bad. Okay, so we flipped those guys, and then we flipped to these guys. So it should be I, J, J, and this is going to be J. It was J plus bottom bound, and then J plus top bound. Oh, minus. And then in here it's going to be I minus left bound and I plus right bound. Okay, that should be right. Frulu, thank you so much for following. Really appreciate it. Money is made up, but important. Generations are also made up, but way less important. I agree with you. Completely agree with you there. Money's also one of those things that I think people put too much power in. Does that make sense? Like, okay, so when you think of successful people, okay, I don't mean to generalize. When people in general, I don't mean to generalize, then immediately say, when people in general, my point is, in general, when you think of successful people, a lot of times you think of people who are very rich, and you tend to think that rich people are successful. Now, again, you here does not mean you in particular. It just means that, you know, when I'm talking to people, they tend to think that a successful person is a rich person. And in some sense, I suppose that is a merit of, like, you know, if you are successful, you could get a lot of money, but also there's so many other metrics to success, and it kind of bugs me, you know, when people are like, you know, when they say things like, you know, if you're saying I'm going to be doing this research or something like that, and people are like, okay, but how much money does that make? And I'm like, well, I mean, who cares about money? Like, we're fundamentally pushing the boundary of human knowledge forward. Surely that's, you know, successful enough. Anyway, I don't know why I'm ranting about this. I'm mostly talking about how we assign value to pieces of paper greater than the intrinsic value of the paper. Yeah, I agree with that. I think money buys freedom. You can do whatever you want with your time. I think that's true as well. I agree with that. Okay, so how are we going to do this bounds check? We know the size of the filter, and we're going to specify that all filters must be odd, is what we're going to say. Just, it's 1, 3, 5, 7, something like that. Does that make sense? Is that okay? I'm going to say it's okay because we need a center pixel, and so we're just going to say it's 1, 3, 5, 7. It's always going to be odd, and that's just what we're going to do. Okay, so in that case, we have a filter, and we're moving the filter along I and J, which means we know the filter size. So we should be able to have a filter width, and I think what I can do here is I can add in a filter width. Okay, so now what we're going to say is if the bound is less than 1, which means we are, let's see, so we don't want size the filter over 2, we want I minus filter width. In fact, we can just do a bounds check on I and J with the signal. So instead of having a bound, we can do we even need a direction? I think we do need a direction. Okay, so now we're going to do signal I, J, the filter width, and then the direction. And then we're going to fix it down here with the bounds check. Okay, So Francisco, make directory. Thank you so much for following. Really appreciate it. Okay, so let's see. As far as money buying you time, I do agree with you that I agree with you there. It's just what I've been getting frustrated with is that a lot of people, right? The most precious resource you have as a human is not money, it's time, right? It's the amount of time that you spend devoted to a particular topic. And, if you are accruing wealth, you're spending your time getting money, that's fine. But, you have to realize that that money costed you, for if you get paid $7.50 an hour, whatever minimum wage is, it costs you a lot of money. Or it costed you a lot of time to get that money, right? So it's just important. I always think of, like, whenever I'm like buying a sandwich or something, I don't think of it as, this is a $4 to $5 sandwich. I don't really know how much sandwiches are because I don't actually buy sandwiches. But just assuming I go out and buy something, I think to myself, how much did I spend getting the sandwich? It's not $5. It's 10 minutes of work. Or I guess in my case, it's about 20 minutes of work for a $5 sandwich or something like this. So it's just, it's something to think about, right? Like your lunch break is an hour of time, and you're spending an additional 20 minutes of time, like on the food. So I don't know. If you can do what you're passionate about in life, that's success. I think that's probably true as well. Standard Pow, thank you so much for following. Really appreciate it. As a Disney villain once said, freedom takes green. That's true. What kind of sandwich? I don't know. Well, when you see some color, there's actually no color. There's only some wavelength and frequency of the electromagnetic wave. Color is only interpretation made by your brain, so it's also kind of made up. I guess, yeah, I could see that opinion. I could definitely see that opinion. Okay, so here we're going to say the bound is going to be equal to, I guess it's going to be, what is it going to be? What was the bound over here? So it was I minus filter size. So I guess I want to do, I think we're just going to have index. All right, this is going to be a really weird, let's just do index minus filter width. Okay, and we say if bound is less than 1, we're going to return, we're going to return filter width. So if it's less than 1, then we have to return filter width, which is going to be, 2 to the left, let's say. So it's going to return filter width, minus bound. I got to think about this. It's not bound exactly, right? It's going to be 1 minus bound. Okay, so what we're checking for right here is going to be this case over here where we're off the bound over here. So that means if for example, our filter width is 0 or our bound is 0, then what we want to return is not 2, but 1. Okay? So what is 1 in this case? 1 is going to be, so if the bound was, let's say the bound is actually -1 instead. So let's say this is -1 here. Okay. Then in that case, we'll say this is 3. So it's going to be the filter width plus the bound difference plus, wait, I'm so confused. Give me a second. So if it's -1, -1 minus 1 is going to give you -2. So I think it's going to be -1. So that's the bound. So it's going to be -1 minus 1. Oh, I had it right. -1 minus 1. And then we're going to add that to that. So it's going to be -1 minus 1 is going to give you -2. So I had it right before. -1 minus bound was correct. I don't know which one's more confusing or less confusing, but that's okay. So we have one done. So now let's talk about the other bound where it's on the far end. Okay, so in this case, we have, let's say this is 2 over, and we have a central point here. What we want to do is filter width -2 again. So in this case, it's going to be return filter width. Okay, so we start with filter width, and then we're going to have to do minus size of signal. Okay, trying to think about this really quick. Size of signal. I think it's going to be bound minus that. Oh, no. Size of signal minus bound. Okay, so if the bound is 100 and the size of signal is 98, then this will give you, it's going to be filter width, so it's 100 minus 98. No, that'll be 98 minus 100. So this will be bound minus, that should be right. Okay. So in this case, bound is always going to be negative. So, right. We want that to be positive. In this case, bound is always going to be positive. Okay, good. This should make sense. Now we just have to get these bounds, these bounds checks done. So I'm going to take a quick break. Let's take a look at chat again, and then we're going to keep going. So what are you making? Yep, I'll answer that once I catch up with the rest of chat. I might have a good lead for an internship this year, but it's weird. After an interview, they are not sure they want to take me in, but they care enough to create something that they never tried before to know my implication is interesting. Thanks to lockdown, apparently. Oh, actually, that's kind of cool in a way. You could go very far down the rabbit hole, but I tend to draw the line somewhere. Sorry for the long message. No, it's cool. I appreciate that. Thanks for sharing. Is this what you're working on? In some ways, yeah. I think we are working on the kernel there. Yes, so we're working on this immediately, and we're just going to be doing a Gaussian kernel. The issue is right now our kernel could be a variable size, so we're just dealing with the variable size kernels, and then we got that. Now, what are we doing in general? If you look at this image up here, in fact, let me again just go to this image, or maybe this image in here. This is basically a set of different function systems put together. So we have one function system to create a heart, and then another function system to rotate that heart. If you see, we have like a little mini heart in here, and maybe another mini heart in here. So you can kind of see it kind of coming out here. So the idea is that we have a bunch of hearts kind of put together, rotated and enacted with all these different function systems and stuff like that. So the goal right now is to basically combine all these function systems and make a pretty image by following what's known as the Fractal Flame method. The Fractal Flame method has a convolutional kernel near the edges over here in order to basically allow for a blurring effect. And so what we're doing right now is we're basically allowing for that blurring effect. Now, the kernel will actually change size depending on the number of points. So if there are very few points around, the kernel will be very large, basically blurring these areas out here. But if there are a huge number of points around, then instead it's going to be very sharp. So we don't actually lose any of the definition in here. So the idea is to kind of blend out here, but not blend in here. So right now we're just getting started by introducing the Gaussian kernel that will allow for the blurring. And then from there, we're then going to basically allow for different sized kernels, right? So we're dealing with edge cases right now. And then after we deal with those edge cases, we should have the ability just to blur an image. And then once we can blur the image, we can then we'll deal with the different sizes. Now, I know what you guys are thinking. Why not just, use an inbuilt, kind of kernel convolutional thing, like some sort of image filter library? We can do that, but because it's a variable sized kernel, it will get kind of complicated, and we do have questions about how to parallelize this in the future. So I figure let's just go ahead and bite the bullet, implement our own convolutional kernel. It's not going to cost us too much performance because it's not a particularly slow part. And we know how it works and stuff like that. So I'm happy to do it. I think this is actually kind of fun. So yeah, I think I'll leave this one up for now. I like this image. That's a nice one to have up. Okay, gotta go. Long day tomorrow. See you, Trash Talk. Have a wonderful evening. Thanks for coming in, and yeah, get some sleep. Oh, for those of you guys wondering, I will be streaming for basically 2 hours from 6 to 8 p.m. tonight, tomorrow night, and the night after that on Thursday, which is Thanksgiving for most people in the U.S., for everyone in the U.S., I guess. I will have the day off, and I'll be spending some time focusing on probably Quiltify. I don't know. I'll probably do a long stream on Thursday and Friday this week, and I really am trying to do long streams over the weekend. I've just been horrible at it. I've just been down. It's hard. Anonymous Tier, thank you so much for the 7 bits, and also OBWOO, thank you so much for following. Really appreciate it. I gotta go, long day tomorrow. Let's see. Bye. You eating turkey on Thursday? I will not be eating turkey on Thursday. Knit the Wiz, thank you so much for following. But you know, for anyone who is eating turkey, I hope you enjoy it. I guess I don't really know. What am I supposed to say to that? But yeah, it's a tradition to eat turkey on Thursday. But I won't be because a number of reasons. One, I'm not with my family, and with the pandemic and everything, I'm not intending to visit my family over Thanksgiving. And the other reason is that I'm a vegetarian, so, you know, I don't tend to eat, you know, birds. Not that there's anything wrong with eating birds, it's just I don't. Okay, so let's get this bound check figured out. So it's going to be this, and then and then filter width, which we will define here. Okay, and let's just go ahead and put the filter width in for all of these guys. Sure, there, yep. And this is just going to be I and J. And in principle, this should be what we need to run. And then we just have to define what filter width is. So filter width is going to be the number of pixels to the left and to the right of our filter. So what I want to do is I'm going to say filter width. Filter width is going to be equal to size of filter in any direction because it's square, divided by 2, and now we're going to floor that onto an int. Something like that should do. Let's just see if this runs. Who knows? It's one of the great mysteries of life. So let's go into here. Now, I'm also going to take this convolutional sweep. Let me just move this into... Yeah, let me just move this into the main convolutional function, the fractal convolution function in here. There's no reason to have this in a separate... There's no reason to have that in a separate function at this point in time. So n is going to be size of out. We have n defined as size of signal. We have out as array. This should all be fine. So I think we can just remove this function entirely. Because basically the fractal convolution function was entirely that convolutional sweep function. There was no reason to have it separate. So we're going to write that, and let's see. So we should have some sort of 2-image something. Here's fractal convolution. So if I just go over here and I run the last flamify, see if it runs. Who knows? We'll see. I don't even remember what we're doing. Error, dimension mismatch. Arrays cannot be broadcast to comma size. Got dimension with lengths 3 and 5. Okay, good. So this is the dimension mismatch that we kind of expected this. So let's see. It's going to be on line 32. It's going to be residual sum. Aha, this is because I'm dumb. Okay, that's because we need the filter to also have... Right, okay. So we have to make sure the filter also has its bounds set appropriately. Okay. So we're just gonna do that. So we're gonna move this down to the next line. Something like this should be fine. And then we're gonna say filter, and it's not gonna be IJ anymore. It should be filter width. Let's see, probably plus bottom bound. Let's see, is that right? Filter width is gonna be. So we're looking for the third element. So it should be filter width plus 1 plus bottom bound. No, wait, what? Oh, no, it should be 1. Okay, I got to think about this. I think actually I got these mixed up. I think it goes from the top bound to the bottom bound. Not the bottom bound to top bound. Okay, we definitely have these bounds mixed up. Like, there's something wrong with our boundary conditions. It's going to take us a while to fix, and that's okay. You know, life is hard sometimes, and this is one of those times. And that's okay. So we're going to do filter. Now we know the bottom bound is going to be, let's see, the filter width. So it's going to be J plus the bottom bound. So in principle, what I'm looking for here, you have a bottom bound and a top bound. So it's going to be filter width. So can we just do, I think we're looking for the middle element. So I think that's going to be, I should think about this. Yeah, for sure, you're right. I'm really fascinated by our perception of reality. The first year in my med school, we did the blind spot experiment. It just blew my mind. One thing that kills me, or doesn't kill me, but one thing I'm super interested in is synesthesia, the blending of the senses. So you can like see smells, or you can taste shapes, or something like that. It's something I've been super interested in. I've read quite a few books on it as well. It's really cool. I'm such a big fan of things like that, where people like fundamentally perceive the world differently. I think it's just really cool. I wish, like, in some sense, I really wish like I was able to look through someone else's eyes, because I swear that other people perceive a different blue than I see. Like I know that's true. Like I cannot imagine they see the same colors as I do, but you can't check that. There's no way to check it. You know? So it just seems so weird to me that like your eyes would naturally wire the same. I mean, I guess you have color perception when you're born, right? I don't know. I end up rambling about this, thinking about it too much, and it really doesn't matter. Stuff like this really doesn't matter. But I end up spending way too much time thinking about it. Okay, so filter width plus 1 is going to be the center element, and then we're going to do add filter width plus 1. So what is the bottom bound? The bottom bound is going to be 5. Let's say the bottom bound is 5. So the top bound is going to be, the bottom bound is 1. The top bound is 5. So what are we going to do here? We know that the bottom bound is going to be, oh gosh, the center element minus the bottom bound. So we're just going to say center minus bottom bound. Okay? And then it's going to go for till center plus top bound. Okay? Then it's going to go from center minus left bound to center plus right bound. Now, note, this is different than this one, so let me think about this. So it's going to be J minus bottom bound. I think it should be minus and plus again. I think I got these mixed up. Okay, so now let's define center. And it's gonna be, let's just call it center. Whatever. Sure. Okay. Well, let's see what happens when we run it again. It's gonna fail. It did. Okay. Attempt to access 3x3 array at indices 2 to 2 and 0 to 4. Okay. So what are we doing here? So we're doing a convolutional kernel. Let's take a look for fractal convolution in here, and we're doing it with fractal convolution with image. Oh, okay. Well, I did that one wrong, didn't I? Okay, that's fine. So we are going to do a filter, which is size 3x3, which is fine. And says attempt to access 3x3 array at indices 2 to 2 and 0 to 4. Okay. Well, right. We've got some debugging to do, and that's totally fine. First thing I'm going to do is actually just print line I and J. Print line I, new tab, J, and just see where we're failing here. It's 1,000 by 1,000 image. So let's see, we're going 1. We've done a few elements. 1, 1, 2, 1. Oh, Okay. That's because this should return filter width. Try that. Okay, we actually got really far. We got all the way through the first row of elements. That's pretty good. Is this Temple OS? No, it's not. I know what you mean. I spend a lot of time with thoughts too. That's why I picked neurosurgery for my residency. Yeah, so when I went into my PhD, I actually wanted to go into neuroscience at the time. But I didn't. Attempt to access a 1,000 by 1,000 array at so we're bounds erroring out there too. Jelly Toast Sailor, thank you so much for following. Really appreciate it. As far as Temple OS, this is not Temple OS. It is actually Arch Linux, by the way. Just letting you guys know. With OpenBox. It says it right there, and I just didn't read the chat. Let's see. But yeah, so I like the setup. It's no one else has my setup unless I've given it to them. Mr. Grandy, thank you so much for following. Really appreciate it. But yeah, it's a very simple open box setup with, I just use 3 colors, black, white, and then I think it's hashtag 575757, but I might have changed it to 878787. It's basically black, white, and gray. These were just the colors I chose, and I wanted a very simple setup, so I made the simplest possible setup, creating my own open box, theme and everything to go along with it. I was thinking about maybe exporting it as well to like the general open box users, but I didn't. It's available in Discord. If you check out Discord, there's like a pinned something on general or something with information on the theme if you're interested. I'm programming this on GPU. It's not GPU accelerated right now, but we will be GPU accelerating it hopefully later this week. Right now we're just kind of getting through the algorithm. And then once we get through the algorithm, honestly, once we have the variable filter width and everything like that, I think that's the stage where we're going to start working on the GPU stuff. So then we'll do stuff with what's known as kernel abstractions, which will actually allow me to write code that can be executed both in parallel on the CPU and on the GPU at the same time, and do both efficiently, right? Because a lot of times when you have these things that will do one or the other, it doesn't do it very efficiently, but this will do it efficiently on both. So I'm pretty excited about that. And yeah, we'll see how it goes. Okay, so what's the issue here? It goes from 1 to 1 at index 1 to 1, and then 999 to 1001. Okay. Okay, but we are grabbing 3 elements. Okay, this means the top and... I gotta think about this. I gotta think about this a lot. Let me just output all of the bounds as well. So we're just gonna do yank, actually dd, and we're gonna paste it down here. Open that up, and let's just output all the bounds. All right, you guys are just gonna have to deal with my print line debugging here, and yeah, sorry about that. So left bound, new tab, right bound, new tab. Let's see, top bound, new tab, and then bottom bound. And that should be right. Okay, let's run that again. Okay, so, okay, we do know for a fact that all of these bounds are wrong. All of them. They're all wrong, which is great. All right, perfect. The top bound, so let's see, it's left bound, and then it's right bound. Okay, and then it's top bound and bottom bound. Ideally, if we're in the middle of the image, this should return all 2s, but it's not. So let me also output, before any of this, let's just go ahead and comment this out for now, and let's output the filter width, just to make sure we're doing this right. So let's print line over here, and the filter width is 1. Oh, because it's 3 by 3. Of course, it's 3 by 3. The filter width, we're fine. Okay, everything's fine. Everything is perfectly fine. Okay, so now we're gonna do, run that again. Okay, good. So that means the left and right bounds are correct, except for the fact that they're returning the same thing every time. Okay, so now I understand it. I'm kind of understanding the issue here. So the bounds check here is, it's going to be the index minus the filter width, but in actuality, it should be the index minus or plus the filter width. The bound is going to be the image, so it's going to be image. So let's just go up here and we're just going to say if the index minus the filter width. I see. We also need to define the actual bound. So maybe we just do this, index. And in here we do index. And then in here we're just going to say I, so this is going to be the left bound, so minus filter width. Filter width, and this is going to be I plus filter width. Oh no. The spacing is all wrong, so we're just going to do this, and you guys are going to have to deal with it. So it's going to be J, it's the top bound, so this should be J plus filter width. And this is the bottom bound, so it should be J minus filter width. Check that and see what we have here. Undefined bound not defined. That is because I'm dumb and I typoed everything, and this is why I should just learn to be better. Try that. Okay, we're running. I think it's doing something. Okay, now we have way too many print lines, so let's just Control C really quick, and let's scroll up. So to check these bounds here, so at 1, the 1 index is on the X, so it's XY, so that seems correct. 1,000 is correct. Perfect. Okay, everything seems correct. We seem to be getting the right bounds here. So let's go ahead and remove these print lines down here, and let's just play around with it a bit, shall we? Then I'll answer the question. Someone asked what we're doing today. I'll answer that in just a second. Run that. And let's go over here. Run that. And see what image. See if it outputs an image. That's all we're looking for. Good, it does. Unfortunately, in contrast to real scientists like physicists, chemists, computer scientists, we are not trained to solve abstract problems. Surgeons are more like some electronics technicians who can remove a big tumor from patients' GPU, occipital lobe. Well, okay, to be fair, like, there's actually a lot of... So I used to read a lot of medical literature when I was, you know, I don't know, when I was younger, I read textbooks. That was what I did. And look, I know that it's weird. I realize that only nerds read textbooks. I get that. But I will say that there's certain mechanisms to how the body works that makes it very much like programming, or more like circuit design or something like that. It gives you the same feel, you know, like in a lot of ways. And I think it's really remarkable how you can kind of boil down like the human body to like kind of objective mechanisms that work in certain ways. You know what I mean? Like, you know, for example, the brain, you can actually remove part of the brain, and all of a sudden the other neurons just learn to, for example, you know, take over the actions of the neurons that died. You know, it's remarkable some of what people can go through and how we understand humans, you know? Like, it's weird. I'll let him answer that. Wouldn't it be a little bit easier if the syntax were highlighted? I see the kappa. I know you're being a bit sarcastic there. We've had this discussion before. Syntax highlighting hurts my ability to read code, so I don't use it. A lot of people like syntax highlighting, and that's totally fine. Like, it's up to you. Here on my channel, where we're doing my stuff, we don't use syntax highlighting. You can go to any other channel on Twitch if you want to see syntax highlighted code. Here, no syntax highlighting. What are we doing today? Let me go and take a look at this image, and then we can talk about it. Mirage, check.png. It's black. I don't think the image worked. Oh, that's because we only had 2 pixels. Oh, let's increase this by a factor of... There. Okay, let's see what happens. Come on. Okay, not bad. Let's go again. Give it a second. Okay, Mirage check.png. We're getting something. And is it blurred? I can't tell. Oh, it is. Yeah. Okay. Woo. Okay. I'm actually pretty excited about that. So let's go down here. Let's actually increase the size of this kernel to be. Oh. We'll do that next. We will do that next. For now, let's talk about what we're doing today. Is the hidden Mandelbrot in there? Okay. There's some clamping issues going on here as well. I'm gonna have to figure that one out. Exactly why it's doing that. Probably has to do with how we're blurring here. Okay, so there's two things we have to deal with. One, why is our image not writing out correctly? That's one thing. And the other thing is how to define this filter for variable sized, like for filters that are bigger, right? So how do we get this Gaussian? Right now it's just 3x3. Let's make it bigger and smaller. Those are the two things we're going to do, and hopefully by the end of the day we have all that set up, so tomorrow we can actually do the variable size filter or whatever. Okay, so what are we doing today? Good question. Thank you so much for asking. Really appreciate it. Okay. So do you see this image in the upper left-hand corner? Well, now you don't because it's in the center of the screen, but before it was in the upper left-hand corner. Anyway, the point is we have this heart thing, right? It looks like a heart. And if you look closely, you'll see that the heart is actually projected in here as well. So we have another heart, and there's another little mini heart in here. And the idea is we've taken this heart shape, which is a single function, and we've applied another function to it, which adds a rotation to it, and another function that adds like a horseshoe-like object. We've added a bunch of function systems together that all do different things. And the idea is by combining them all together, we can create these really cool and just interesting images. And this is the heart of the Fractal Flame method. Right now what we're doing is we're perfecting this method. We're implementing the rest of the algorithm such that, you know, we don't see these pixels over here being so grainy and stuff like that, but we still see sharp, like gradient. So we still see like the sharp edges in here, but we don't see the graininess out here. And so that's why we're implementing a Gaussian blur kernel so that we can do that. And we've got a few other things and tricks that we need to do before I would say that we're done with the method, but we're getting there. We're getting close. And so once we have this fractal method already implemented, what we're going to do next is we're actually going to basically try to map a set of fractal flames onto any arbitrary image that we read in. So the idea is that, you know, the first thing is we have to generate the images, which right now takes a long time. But after we generate the images, we're then going to have to put on top of that a gradient descent, rather a genetic algorithm that allows for us to then find kind of like the best set of fractal flames in order to recreate that image. So literally, I want to have an image. I have a specific image in mind where I want to put my face down, like as an image. I want to read that into our code. And then I want to output a set of fractal flames that closely resembles my face so that I can literally become a fractal. That's the point. I want to turn into a fractal. And I know that sounds really weird, really trippy. I don't know. It's been a dream of mine since like 2 weeks ago when I hatched this idea up. And I've been thinking about nothing but this and a video that's coming out in 2022. There's a video that's coming out in a very long time. But anyway, the point is, yeah. That's kind of the whole plan. I'm sorry if I sounded a bit manic there. It's what we're doing. So, because we're going to have to do like some sort of cost function analysis and stuff like that, again, gradient descent, not gradient descent, but, genetic algorithms require a lot of iterations. That means we're going to have to do a lot of fractal flames. And because of that, we're probably going to have a relatively quick runtime for all the fractal flames. So we're going to have to parallelize it on the GPU. We got a lot of stuff to do, but again, right now we're just in the infancy, just generating these images. So what we just generated was where is the image? This image in here. Now this image is very similar to this image, right? I think it's rotated for some reason. I'm not exactly sure why it's rotated. But they're basically the same. What I liked about this image is that if you zoom in, you'll see that all of these little pixels are actually crosses, which means we've actually blurred the crosses. We've blurred the pixels a bit, which is great. So now we need to make a variable sized blur kernel and stuff like that. So sorry, I'm not doing a very good job of describing this, but long story short, we're getting there one step at a time. Cardioid. Yeah, I guess it is closer to a cardioid than a heart. It's just the function's called a heart. By the way, El Manu 2010, thank you so much for following. Really appreciate it. Okay. So what do we want to tackle first? I think the first thing I want to tackle is why this is happening. Why are we getting a nan? That's my number one question. So let's go ahead and try to tackle that right now and see if it's in this convolution function or not. Nope. So I'm just gonna run this, and we did not get an and there. So for some reason, when we're doing our convolution here, and I know why, we are not outputting the right color. So here what we're gonna do is we're gonna do the residual sum, which is gonna be equal to all of this. But what we need to do is then we need to normalize the image after it's all done. Because right now we've got like red, greens, and blues that are beyond 1. Or maybe for some reason nans, and I'm not exactly sure why it would be a nan. But we're for some reason getting nans, potentially. But we are doing the right computation. So the question is, why are we getting... I'm guessing that it's not clamping a nan. I'm guessing it's clamping a value above 1. I think that's the actual issue here. So we just have to make sure that when we put everything together, it scales appropriately. So what I'm going to need to do is have like a normalized image function. And we're just going to go through all the pixels and just normalize it at the end. So functions bound check, we need that. So let's go up here and let's do function normalize. Sure, and it's just going to read in an image, which is going to be an array of type C. I think C2 specifically. Sure, and then we're going to say where C is a union of RGB and RGBA. There's just 2 different color types. In principle, we can also have HSV and stuff like that, but whatever, it is what it is. So here we're just going to go through. And the problem here is that we have R, G, and B. And so do we need to normalize each individual color channel? Maybe that's what we need to do. Yeah, maybe that's what we need to do. I'm not really sure about that. But for now, I'm just going to put a to-do in here. Maybe normalize. How do you normalize colors? So we're adding them all together, which is fine. Yeah, okay, we're just gonna normalize R, G, and B separately, and we're just not gonna worry. Maybe normalize channels all together. Oh, hello. Not separately. Question. Okay, so in here we're just gonna say, I guess we're just gonna find the maximum. I don't know if there is a maximum function already defined. So let's just see what we can do here. I'm gonna create a value of A is gonna be equal to RGB of 0, and then RGB of 0. And let me just see what happens if I do, let me just see what happens if I do maximum of A. It's probably not gonna work. Now let's try it again. Okay, it doesn't work because there's no method for is less for RGB normed. Okay, that's fair. That's kind of what you expected. For people like me, not computer scientists, Simulates is making cool pictures by a complicated rocket science-like method. It's very far from rocket science. It's probably a bit more complicated than that. Rocket science is rather trivial. I'm joking. Okay. So how about we just do it ourselves? Screw it. It's not a big deal. So first, finding the max of each color channel. All right, max red, max blue, max green. Sorry, this is so dumb. Oh, sure. I misspelled green, for Pete's sake. Here I was saying rocket science is easy, and like, I can't even spell green right. Okay, so we're just gonna go through all the values in the array, and so we're just gonna say, for I equals 1 to length of image, and here, and I think we're gonna normalize with an exclamation mark here. So normalize image. We're then gonna say, if image of I dot R is greater than max red, and here, and then we're going to say max red is equal to image of I.R, and now he's do the same for. Oh, this is the dumbest thing ever, but it's okay. Red, green, and blue. Sure. Green, and then we're gonna do max red, green, and then blue. All right, add some spaces in here for fun, because who doesn't like space, you know? DD and P up here. Okay, so now we're just gonna divide by. So now we're gonna say, can I do A of colon dot R? No, I can't do that. Blue has a minus, not an equals. Ah, thanks for that. Blue has a minus. Wait a minute. Maybe it's on my screen. It seems fine on my screen, but maybe I'm just being dumb. Okay, so now we're just going to divide by. So now we're going to say, we're going to have another loop for, for I is equal to 1 to length of image. Again, this is not the best way to do this. I'm just doing it for now and whatever. Length of image. And here, and we're just going to say image of I.R is going to be divided by equal to max red. And then we're going to do the same for green and blue. All right. So now what we have to do down here is we're going to try image, and now we're going to say normalize image and see what happens if we run this, and hopefully we don't get the same bounds error. Set field immutable struct type RGB cannot be changed. CK Game Dev, thank you so much for following. Really appreciate it. Are all three are still compared to max red? Let's see. You're right. All right, let's fix that one. Green and then blue. See, this is why I have to stream all my programming. Otherwise, I make really stupid mistakes like that. My screen then resolution problem. Do you think deep learning is a syncing chip? No earthly idea. I don't do deep learning. Is this free BSD? No, this is Linux. I use Arch Linux. So my exact setup is Arch Linux plus OpenBox. As far as deep learning being a syncing chip, I'm gonna be honest. I have no clue. I don't do deep learning because I don't do deep learning. That's it. I don't really know what else to say there. So here we're going to say color is going to be equal to RGB of this. I think I can just do C. No, we're going to have to do RGB of this guy divided by max red. Then we want this guy divided by max green. Ooh, does it fit? I think so. Maybe not. That. Yeah, we're gonna have to move that down to the next line. So let's just move all three. Here. And there. And then finally we're gonna say image of I equals color. There we go. All right, let's take a look at that image. Okay. Did it work? Yeah, it worked just fine. Perfect. Okay. Let's see. Nice. I've never seen Arch looks like this. Generally, this window managed format is why my BSD environments look like. Nice channel, by the way. Oh, thanks for that. As far as BSD versus Linux, I'm gonna be honest. I don't really know so much about the differences. I know that a lot of people really like like BSD a lot. I've just always been an Arch Linux guy. Arch Linux was my first ever non-Windows OS, and you know, I kind of got used to it. I ended up, like, when I was 14, I just decided, you know, screw it. I don't like Windows anymore. It was Windows Vista was out at the time. I just bought my computer. I was pissed at how slow it was and everything. So then I install Arch Linux. You know, it took literally 48 hours without sleep because I didn't even know how to burn a disk. But after that, I don't know. I felt like I genuinely knew something. Like the install was quite challenging, so I felt like I knew my system very well after that, way better than I did when I was a Windows user. So I ended up just, I don't know. I ended up gravitating towards it, and a lot of things about the Arch philosophy have become ingrained in like who I am. You know, I know this sounds really lame and like whatever, but the idea that you always want a simple solution, not necessarily the easiest solution, is something that I live by, you know? Like, part of the reason I'm a vegetarian, outside of the fact that for some reason I can't digest meat very well anymore, is because it's easy to minimize dependencies by removing meat from your life, so why not remove meat from your life? You know, it's easy to remove cell phones from your life, so remove cell phones from your life, you know? Like, don't do anything complicated. Just do the simplest possible things, even if it makes your life a little bit more complicated. It's simple and understandable. You know what I mean? I don't know. It's kind of a weird rant, but like a lot of people conflate simplicity with easiness, and I think those are two completely different things. Something can be incredibly simple, but also make your life miserable, right? Like, for example, having a hatchet to cut down a forest. A hatchet is definitely a simpler tool than a chainsaw, but you know, chainsaws make your life easier. So you live with the complexity of the chainsaw because your job is cutting down forests, right? Now, admittedly, that might not be the best idea to use that analogy, but because, you know, environmentally friendliness and stuff like that. But you get my point, right? Like, the way I see it is my system is simple. It's not necessarily easy to use, but it's simple. And I like simplicity, you know? Okay, that was a rant that I probably shouldn't have said. I'm sorry about that. Okay, let's keep going. So the next thing I need to do is create a function in here that will essentially return back a kernel of a particular size. So let's go in here and let's just say function, ooh, hello. Function create Gaussian kernel. Okay, what are we going to do? We're just going to read in kernel size. Something like that should be fine. And here. Okay, and we're just going to say if kernel size is odd. 2. Yeah. If is odd. Is odd. Sure. Kernel size. Kernel of size. Oh. Print line. Even kernel sizes are not allowed. New kernel size is, and let's just do kernel size plus 1. Well, let's do minus 1. Yeah, that'll do. And now we're going to say kernel size minus equals. Okay, there we go. Let's see. I don't know if I said thanks for following Kalmata001, but I appreciate it. Makes sense, though I love the simplicity of Arch installation as well. Right, I don't know. I've got weird opinions. I know I have weird opinions. I should stop having weird opinions, but it's really hard to stop having weird opinions when you have a lot of weird opinions already. Bilge, thank you so much for following. Really appreciate it. Okay, so how are we going to do this? We are going to create a Gaussian, and we're going to cast that Gaussian onto a kernel of a particular size, and this is going to be a pain. Hey, C252, how are you? I hope you're having a great day. Okay. Now we know Gaussian kernels aren't hard. We know how Gaussian kernels work. They're easy. There's a definition for a Gaussian kernel that we know and love already. So let's just mess around over here in the REPL, and then we'll go from there. So what is a Gaussian? It's a good question. Thanks for asking. So Gaussian is usually going to be, so let's just go ahead and do using plots. And let's just plot it out in 1D first, and then we'll do a 2D, and then we should be able to turn that into a kernel. I don't know. Let's just see how this goes. I have no idea. Okay. Pre-compiling plots. And then this shouldn't be hard. We do Gaussians all the time. It's relatively easy. So it takes a while to pre-compile plots. So if you guys have any questions, comments, concerns, let me know. And we'll talk about it. Otherwise, we'll just sit here and be awkward. I'm pretty good at that. It's it's my calling, really, just sitting in a room and being awkward. So, oh, we also want to make sure this array is normalized, but I think that should be easy enough to do. Yeah, I think that should be easy enough. Okay, so we're just gonna say a is gonna be equal to, it's x squared over some sort of sigma, so it should just be I minus 10 squared exp of this. Oh no. For I equals 1 to 100. Plot A. Oh, it's minus x squared. What's your favorite food? That is a question. What is my favorite food? Man, that is a very good question because I actually don't know. What's my favorite food? I think it just kind of depends on, you know, when you catch me. So, it should be minus x squared. What? Why is that not working? You kidding me? Minus x squared over something. Oh, New York. Wait, what? Where's New York? Is he here? Oh, New York. Thank you so much for the 11 months. I appreciate it. How are you, man? It's been ages. Samuel Cow. How have you been? Oh, I need 11 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that going to work? I don't think that's going to work. I think I need spaces. Does that work? It doesn't work. Let's try that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. Then C252 is 17. Oh, okay, let's try that one again. I'm sorry, I'm acting weird today, guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. In the chat, there you go. 17 female cows. Long time to see. It's been crazy outside in the world. Yeah, how have you guys been? By the way, C252, you also haven't been here in a while. But yeah, New York, how are things? Like, I feel like I haven't seen you since, what? It must have been like, it's been a while. Like, it's been a long while. I hope you're having a great time. I mean, you know, I don't know. I feel like, I don't know. I hope you're having a great time is what I mean to say. But yeah, I'm glad to see you guys here. It's been ages. Okay. So let's see. EXP of negative x squared. Why are we getting imps? Am I this bad? I don't think I'm this bad. I've never been this bad before. Negative x Gaussian kernel definition. This was, people had this in homework because it was so simple. EXP of negative x squared, negative x. Oh, is that it? Is it just that? Now if we plot that. Okay, thanks for, I'm dumb. So let's do I minus 50 squared. Okay, so now what we want to do is have some sort of sigma. So let's do divided by 10. And let's plot that. Okay, so here we have our Gaussian. Seems fine. Perfect. Right, okay. Let's go over here and let's just mess around with this a bit. It shouldn't be divided by 10 there. It should be divided by 10 over here. Perfect. Now we're going to plot A. There's our Gaussian. Perfect. So it should be of width 10, I think. So let's mess around with this a bit more. So we're going to do, A is going to be minus 5. And we're going to do 1 to 20. No, 10. Plot A. Okay, that's not so bad. So 5 in the center here. We know it's divided by 10. So let's see if we divide this by 5 instead. Okay, that looks better. Okay, so this means that we want, in general, we're going to want it to be 2D. So we have to think about how to index this. So let's just kind of mess around with this a bit. But the filter is centered on 5. I think that's right. Okay, we'll just kind of mess with it a bit. Okay. It doesn't matter if it's off by that much. So 4 I is equal to 1 to kernel size And here for j is going to be equal to 1 to kernel size. And end here. Let me catch up on chat. Missed some. Okay, pretty good. How about you? Because the mine should be outside the square. Yep, thanks, Amaris. I caught that. For sure, it's been a month or so. I've just been so stuck in trying to get some research done that I forgot there was an outside world. I feel you. I definitely feel you. Mandalian, thank you so much for following. Really appreciate it. I moved to the more applied field of computer graphics from linear algebra. Oh, that sounds super cool. It's way more interesting as it turns out. Well, right, it depends, but also I kind of understand. It's way more interesting as it turns out. Weren't you in pure math for a little bit? Yeah, I started on pure linear algebra, but found I really liked doing more applied stuff. So they let me move to that since it was still early. Yeah, that's super cool. I'm pretty happy with that. Or I'm pretty happy to hear that. So we're going to say kernel is going to be equal to zeros. And it's going to be a size, kernel size. Okay, great. So now we're just going to define each of these guys. Okay, now I've got to think about this. It should be... So it's x squared, but it's a 2D kernel, right? So it should be x squared, and we should also have a y squared. So is it going to be x squared? Is it just two kernels put on top of each other? I think that's what it is. No, it's x squared plus y squared. What is a 2D Gaussian defined? X squared plus y squared. I was correct. So it should be kernel of I comma j is going to be equal to exp. Let's also define a center. Is going to be equal to floor of int of, oh gosh, kernel size divided by 2, right? Plus 1. That's really annoying. Let's do this differently. Let's do the center is going to be, so okay, what am I looking for here? I want the center of the kernel. This is fine. It'll do. Okay, so now we have exp of, and we're just going to do negative, and then it should be, is it x squared? So it should be negative of x minus center squared plus y minus center squared. Got to think about this really quick. And then I think we need to divide all of that by kernel size, I believe is what I need. And then that should do it. And now we just return the kernel. Okay, let's see what happens. Oh, we have to normalize it. Can I just normalize it? What happens? Normalize. Does that exist? No, it doesn't. Norm. Using linear algebra. Now let's try norm of 1, 1, 1. Perfect. Oh, no, that doesn't help at all. It should be like normalize. 1, 1, 1. Perfect. That's what I want. So we want norm. Sorry, guys. I'll catch up on chat in just a second. Normalize of kernel. That should do it. Start doing pure. Let's see. Should be. See, Amaris, I should really go to sleep. Have a wonderful evening. Hopefully, I will see you later. As far as my streaming schedule is concerned, I will be streaming from 6 to 8 p.m. Eastern Time today, tomorrow, and Wednesday. And I'm hoping to do a long stream on Thursday and Friday. And also, I really need to get back to doing long streams over the weekend. I did them for like a week or two, and then I stopped. But, you know, it's just, you know, life happens. It's a world. 2020 is a year. It's rough. But hopefully, you know, everyone's getting through it, and you know, I know I'm getting through it. I've got a meeting on Wednesday about, you know, potentially a new job and stuff like that I'm pretty excited about. So we'll see how it all goes. Yeah, we'll see how it all goes. So now we should have this create Gaussian kernel function defined. I think I might have to do using flamify again. And now if I do create, that didn't work. Let's just open it up again. Oh, am I not exporting it? Maybe I need to export it. I probably do. So let's go up here and let's just do export, create Gaussian. Oh, or is it already being exported? No, it probably isn't. Kernel. There we go. And now it's using Flamify. Yeah, so the postdoc is it's not that my postdocs, well, okay. I'm coming up on the point where I am about to renew my contract for my postdoc, and I'm wondering if I should renew it or if I should not renew it. So that's kind of where I'm at. Flamify dot create Gaussian kernel. Let's do 5, and we're just going to say A is going to be equal to that. X not defined. X is, of course, not defined because this should be I, and this should be J. Let's try that. And then let's just try using plots and try plotting that. Normalized, not defined. Probably because I have to do using linear algebra at the top here. Okay, this seemed to do something. Is it what I expected? Maybe not quite, but pretty close. So let's do using plots. And then we're going to try heat mapping that. And we should get a reasonably okay Gaussian kernel. It's not the best kernel, but it'll be okay. So let's do heat map of A. And let's just see what it looks like. I think I might want to make the kernel size slightly smaller. 'Cause, I mean, that's pretty good. Honestly, that's not bad for a Gaussian kernel at all. Let's try defining A for a 3x3 kernel. Heat map of A. Again, not awful, but it is definitely a Gaussian. So let's do kernel size +1. Okay, so let's try it again. Okay, so the issue here is that probably let's try ×2. That is not what I was expecting. ×5. Oh, I'm making it bigger. Let's do divided by 5. Okay, that's better. That's kind of what I was expecting. See how it's like, okay, so this is very strongly. Let's do divided by 2. Okay, that's what I was expecting. So now if I heat map this, the scale is such that it's basically 0 here on the corners. Well, not quite, but it's closer. So let's do, how about we have create Gaussian kernel, and we also have an optional argument in here, which is going to be deviation factor or something. And then in here, we're just going to divide by, oh man, my spacing is all off here. Let's just go there and that'll work. And then we just divide it by the deviation factor. Let me move this down to the next line. Something like this, maybe. Sure. Okay, let's try that. And deviation factor is going to be naturally set to be, let's just do 5 or something for now and see what happens. There. Kernel size not defined. Try that again. Okay. Seems fine. So let's try 5. That seems like it is very sharp. Let's try 100. And now let's do a heat map of A. Yeah, so that's very sharp. We probably don't want it that sharp. So let's try with different deviation factors. That's still very, like, you know what I mean? Like, that's not very, I was expecting it to be as clearly a Gaussian, but, it doesn't really fit very well. So let's try making this 10 by 10 instead of 100 by 100. Heat map of A. See, that's what I expected. So, okay. The general question is, how do we create an appropriate deviation factor such that it extends out to the edges well enough? That's a good question, and I don't really know the actual answer to that. So let's just try 20. Do we even need, maybe, okay. Let's just see what happens if we do 5 here. Key map of A. Let's just have the deviation factor set to 1 and just, we can mess around with it a bit later. But for now, let's just mess with what we have and then we'll get back to it. So here, when we have this guy in here, we're going to do create Gaussian kernel. And we're just going to do, let's do 5 by 5 for now. Well, no, let's do 10 by 10. And let's just see what happens. Just, we're really testing to make sure this actually works. Okay, wrote that, and now let's just do the last flameify.flame, see what it looks like. Even, oh, well, fair enough. Okay, so now we're going to do mirage of check.png, and we see, very luckily, an incredibly blurry image. Okay, that's actually what I was expecting. That's pretty good. Okay, so we have almost exactly what we expected. What I'm going to do here is I'm just going to say to do figure out how to select the best deviation factor. Okay, so that is where we're going to leave it for today. Let's see who's live and who we want to rate at the end of stream. Kitboga is live. What are they doing today? Tricking scammers. Of course they're tricking scammers. That's what they always do. Master Mindo, let's see, Go Pirate Software. I almost feel like, look, we never raid Kitboga. I almost feel like we should raid Kitboga, just because I feel like we should. I don't know, he's such a cool guy, and we don't usually raid him that much. Let's rank with here, get status, get add dot, get commit. Oh, sure. Well, let's quit there. Get status again. Okay, now get commit. And we're going to say adding a blur kernel. Next step is to allow it to scale with particle number. Okay, get commit. Dash M. Oh, I just did that. Okay, git push. Origin development. Okay. It's a day. Today's a day. Okay. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I don't know. Should we raid? I feel bad for raiding Kitboga because like he has so many people watching already. He's such a great stream. Maybe we should raid someone who doesn't have as many people watching, like Master Mindo. Anyone else live? We have Super MC Gamer. We could do. I don't know. How about we'll raid Kitboga. So if you guys don't know Kitboga, he does scam calls all day. He's an amazing person. I really like watching his content. I usually raid him every now and again. I feel like tonight's the night that we raid him again. Cyber Rectus, thank you so much for following. Really appreciate it. That's it for the night, guys. We're gonna be back tomorrow. So let's go start that raid on Kitboga. Okay. So that is it for the day, guys. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. Anonymous Cheer, thank you so much for the bit. Really appreciate it. And yeah, I will see you guys around again tomorrow, 6 o'clock p.m. Eastern. 6 o'clock p.m. Eastern. Yeah, that's it. And that's it for now. So bye, guys. Thanks for watching. And yeah, we have a lot more to come. Whatever, you know what I'm saying. Bye, guys.